Cool, I'm kind of paranoid my music is going to be coming through via chat, and I don't want that to happen. So I'm just messing around with settings at the moment. We'll get started in maybe 10 minutes or so. Quick volume check, how's the mic doing? I know we can probably hear traffic in the background, but I can't really do much about that. Cool, let's get started. So I've got my machine, it's already set up to code in Clojure, and that's where we're going to start today. I might do another video on how to set up a machine ready to go, code in Clojure, etc, etc, but until chat is talking to me, awesome. Yeah, I was saying I might do a setup video a bit later, but at the moment I'm just going to dive straight in, and if people have questions, hopefully they'll ask either now or after the stream, and we'll see what happens. This is partly still me learning what's going on and having a bit of fun as well. I'll probably go for about an hour tonight. All hail the Hypnotoad. Right, so the first thing we're going to do is start the new project using Linigan. Linigan is a build and testing tool for Clojure. It does pretty much everything for you, which is really nice. I think it's play CLJ. So here, new is the command. I want Linigan to do play CLJ is the template name, I think, and streaming game is the name of my project. So one of the cool things about Clojure is it has a really powerful templating system for starting new projects. Cool. Cool. No, I didn't make Clojure. Clojure is it's a Lisp built on top of the JVM. I'm using it because I use it a bit at work, and I find it's a fun language. It's very functional, and once you get going, you can be very productive. And because this is like a solo project, I figured I would pick a language I was productive in, rather than maybe the best language for writing games. So starting a new game gives you a whole bunch of stuff for doing Android, iOS exports. We only care about desktop for now. Inside of desktop there is source and there is source common. We care about source common. In fact, if I do nothing else here, just a line run, we should get a basic empty window. So for graphics access, I'm using something called PlayCLJ, which is a library that wraps around libgdx. Libgdx is a game engine based in Java. It gives you access to some OpenGL stuff, both 2D and 3D, pretty easily. Awesome, so we can get a basic hello world window up and running. That's what I wanted to check. Let's dive into the source. And at the same time, in the background, I'm going to start the REPL. So the REPL in Clojure, REPL stands for read eval print loop. It actually runs on the network, so you can send commands from your IDE to the REPL to be evaluated and get the result. What that means is you can hook into lots of the language features, sort of evaluate code in real time, test a bunch of results. there's some basic Clojure code. We know that plus works. Clojure is a Lisp, which means it uses Polish notation. So rather than having brackets at the end, you have brackets at the start. Everything is an expression, and then you can wrap expressions. Up. Cool, and the reason we started the REPL was so that now inside the editor we can hopefully, we can bring up documentation, and what that's doing is it's sending the command to the REPL to be run and then giving us the result. Let's look at what's going on already. I'm just going to lower the volume because I can hear my own voice and it's freaking me out a bit. Right. So we have def screens. Screens are your basic unit of thing that you want to display on a screen. That's pretty clear. OnShow takes a function, and this is the first thing that gets run when your game starts. OnRender gets run every time the rendering loop fires, so that's about, I think it aims for 60 times a second. You can dive in and configure that later, but I'm just going to leave the defaults on. I'll just turn on the cursor line so it's easier to see. Def game creates your entire game for you, packages it up, sets the screen, and sets it running. So what these basically are, these are macros which are provided by PlayCLJ. We don't need to worry about what a macro is now. It's best way of describing it, it's code that will be run before the main compilation happens. But really what these macros do for us is it lets us call into the Java libraries for libgdx very easily, or in a more Clojure style way rather than a Java style way. And because we're writing Clojure, that's what we want to do. So to start with, let's make it a bit more interesting. So we're currently drawing this, let's talk about that quickly. So we're currently drawing this label onto the screen. The way this works is you have a big list of entities, and every time the screen is rendered, it loops through your list of entities and draws every single one. At the moment we only have one, this label, and the contract PlayCLJ uses is every method has to return a new list or an updated list of entities. So what I'm going to do is to make it a bit more interesting, let's draw a shape rather than just a label, or maybe as well as a label. So defn creates a new method. These are the arguments. We'll worry about arguments in a minute. And we want to call, just check my notes. First of all, we want shape. Shape is a method that PlayCLJ gives us. It takes a couple of keywords and it will return something which can be drawn onto the screen as a displayable object. Cool. 0, 0 width height, and sure, let's use width and height as arguments. We'll tidy this up in a moment. So let's change our onShow method to return a list of things. So square brackets are for lists in Clojure, or Clojure actually has lots of different kinds of lists. Square brackets are actually for vectors, which most of the time are going to be perfectly fine for what we want. Let's make this 100 by 100. If you're used to other language or C style languages, or Python, or even traditional Java, actually, it's worth pointing out that Clojure returns the last statement for you. There's no return word. It just actually, because it's a functional language, you generally always return something. You try and avoid having side effects. So if that works, we should have a shape as well as a label. Cool, we have a red square. So there's a bit of a pause there while the game started up, and I can't. It keeps appearing on my other window, on my other monitor. So I keep having to drag it in, or remember to drag it onto this window so people can see it. But we have our shape. Hooray! Let's make things a bit more interesting. So the thing I want to focus on first is doing movement, and doing movement or player movement in a reasonably good way that's going to eventually give us some nice tight platformer controls. So let's change this to actually be the player. So we're going to take X position, Y position, a width and a height. Width and height, that's okay. What we're going to do actually is we're going to use a sock or associate. You can see down there what it does. It lets you set keys and values inside maps. Maps are data structures in Clojure which store a value against a key for looking up later. Play CLJ works by looking, or it wraps up drawable things like shapes inside of maps, and then you store extra information like where the shape should be inside that map. So what's going on here is we're taking the shape object and we are adding a key of X for its X position, a key of Y for its Y position. This rectangle, actually, we want to keep it at 0, 0 because it will just make the maths easier later on. We don't really care too much about that rectangle other than that's what will get drawn, but where it will get drawn is determined by these two numbers here. So this is now MK. MK stands for make. It's kind of something I ripped off from Haskell. Make hero, yeah, let's make the hero 100, 100, and let's have 16 by 32 for now. Or actually, let's do 48 instead. 16 by 48. And if we run that, it will either blow up or we'll have a tiny rectangle on the screen representing our hero. Cool. So we have something on the screen. Eventually we'll have graphics and it'll be all very shiny, but until then we're going to start with a rectangle because what we care about for now is movement and getting some nice movement going. So let's also get rid of our label. So the simplest thing we can do is add in gravity, or cheap gravity. We'll add in nice gravity, like the good gravity we bring out when the guests come over later, but for now we'll add some cheap gravity. So here we're going to use a map. What a map does is it takes a list of things, it runs a function over every item in that list, and it gives you back a new list filled with the results of that function, which is exactly what we want, because for every single and we only have one entity at the moment, and that's the hero, but for every single entity eventually we're going to want to update it. So we're going to put the map in just so we don't forget later. Right. Function entity, and let's just return the entity for now, and we can test that it still works. Cool. So this should still work, basically. Nothing will have changed. Or it will have done because I've broken something. Cool, everything remains the same. Our label's gone actually because we got rid of it, that's what we wanted, but otherwise everything is still working. Awesome, so for every single entity at the moment, we only have one entity, that's the hero, but for every single entity we are going to say, so a sock, this is the same as what we're doing up here. We're just going to replace a value. Entity y is going to be decrement of y of entity. So let's just go over what that's doing in the REPL. So dec, which is sort of in the middle. When you write Clojure, you read it from the inside out. So decrement just takes a number and reduces it. A sock will take a map. This is an empty map, and a key like y, and add a new value. So if we do that, we get back a map with y equals 10. But if we already have a map with y inside of it, what we want to do is take our existing y value and decrease it by okay, so we need to pull this out. So we have some map with a y of 10, and then we're going to take that map, and we are going to update y to be the decreased value of the existing y value. Yay, y of 9. Eventually, I think there's another function called update or update in, which will do the same thing but in a slightly shorter way, but we know this works, so let's use this one. And let's put the player right at the top of the screen. 300. And now we wait for everything to compile/build. Cool, and we have gravity. We are falling down. We're falling pretty slowly, but we are falling. Save. So I kind of have a thing where if I don't know what I'm doing, I just repeatedly save the file until my brain wakes up. Cool. We can fall down, but what we actually want is slightly more, well, not realistic gravity, because realistic physics don't make good game physics, but we want some nicer gravity. Generally you want the player to, or we want the player to accelerate as they fall, so they start off falling slowly, but very quickly they're falling at maximum speed. So to begin with, let's just set up some variables. Max full speed is 2, and gravity acceleration is let's say 0.05, and we're also going to, into the player, we're going to introduce the idea of a velocity. Let's use a map for the moment, and we'll start off with 0, 0. So x velocity is 0, y velocity is 0. Then let's pull out a new function. This function we'll call apply velocity. This function is going to start with an entity, and then it will use the information inside of that entity to move it around. So let is a way of defining or pulling out short-term variables to use inside of functions. So to start with, let x velocity is going to be the x value. So this will grab the velocity out of the entity, this will grab the x value out of that velocity. In the same way, let's do y velocity is going to be y of velocity of entity. So inside of this function now, I can use x and y velocity to refer to these things. And what I want to return is an updated version of the player to start with, or an updated version of the entity. It could be any entity at this point, with neaten that up, a new y value which is equal to y velocity plus gravity acceleration. So let's just do a sense check. Here, this will take an entity, grab out its velocities, and update the y velocity. Does that make sense? Okay, so what we actually want to do is, yeah, if we're applying a velocity, we just want to, let's not worry about this for now, we're going too far ahead. Let's just update this to be y velocity plus the y value of entity. Then down here we can replace this entire function with apply velocity, because map just takes a function and a collection, and apply velocity is a function. So because our velocities are both 0, our player shouldn't move at all. Cool, so our player doesn't move, which is what we wanted. We're kind of back to square one, but we're doing stuff in a slightly nicer way. So now if we set our y velocity to be minus 0.3, this should start falling down very slowly. Sweet. And what we said we wanted was we wanted our player to accelerate as they were falling up to a maximum speed. So let's now add a function called update velocity, which is going to look a lot like our previous one, but what this one is going to do is it's going to update the velocity based on the acceleration we've got going on. So we'll just do it for y velocity for now because that's all we need. Y of velocity of NC. Cool. Actually, we do need x velocity here as well, because we don't want to just overwrite the x velocity. X of velocity of entity. Sweet. So entity x is just going to be x velocity. Do I want to enable dictation? No. Y is going to be yeah, we want to update the velocity to be a new map with these things inside. Y is going to be y velocity plus gravity acceleration. Shove that on a new line, tidy that up. Very nice. Quick sense check. This is going to take an entity and grab its existing x and y velocities, and then it's going to set them to be new. Set the y velocity to be a new value based on the acceleration due to gravity. And that should be negative because we want the player to fall down. So I think we can probably start the player a bit higher as well, just to check to see if this works. Right, we now want to run apply velocity and update velocity at the same time. So we're going to turn this back into a function inside of our map. Again, map takes a function and a list of things, applies the function to every item in the list and gives you back a new list based on the results. So what we can do here is we can take the entity, we can pass the entity into apply velocity, and we can pass it into update velocity. Awesome, and hopefully what we'll see is our player will start to fall and they will accelerate as they fall. Cool, hopefully people saw that I was a bit slow in moving the windows around, but there was definitely some acceleration. So the next thing we want to do is only accelerate up to a maximum point. And the reason we kind of care about acceleration and velocity, etc., is because it will make jumping and kind of advanced movement physics easier later on if we do it right to start with. So inside of update velocity we can actually I'm going to define a function here which is going to be useful later called clamp, which will, no I'm not, we'll worry about that later. We'll worry about clamping when we need clamping. Instead, down here let's just say what's the neatest way of doing this for now? Right, down here let's say new y velocity is going to be basically this here. So let's move this up here. Then when we update y, we're going to say if new y, if new y velocity is greater than, what did we call it? So max fall speed. Max fall speed. Then we're going to set y to max fall speed. Great name, great name. And then if not, we're going to set it to new y velocity. And we can't use greater than because at the moment we're falling. So let's get the numbers right. We're going to say if new y velocity is less than max fall speed, then we'll set it to max full speed. Otherwise, it's okay to set it to new y velocity. Let's move the player up even higher, run this, and see if it explodes or if it works. Cool, there we go, we're speeding up, we're speeding up, we're speeding up, and I think we're pretty much constant by the bottom, which is exactly what we wanted. Nice. Right, now let's worry about x and y. Or rather x and also x, moving left and right. So the way we've got our axes set up, x is left and right, y is up and down. Now, the simplest way of doing this for the x value is to set x velocity based on whether keys are pressed, and we can do this using a condition statement. I'll just check my notes. Yep, I have notes. So to start with, we're not going to have any acceleration, we're just going to have kind of an infinite acceleration, so you're either moving or you're not moving. Eventually we'll probably change that, but just to get something that works. Because it's all about getting the next smallest thing that works, and then just updating. Keypressed. Keypressed is a function from PlayCoj that surprisingly tells us if a key is pressed. So x, if the A key is pressed, then we are going to set x to -1. This is in, yep, update velocity, this is what we wanted. If the D key is pressed, we're going to set x to 1. Otherwise, there's a value you use here when you want this to fall through, and I've forgotten what else. That's it. Else 0. So this will, if the A key is pressed, x is going to be -1. If the D key is pressed, x is going to be 1. Otherwise, x is going to be 0. That sounds pretty reasonable. Now, in apply velocity, we do actually care about our x velocity, so let's add that in as well. X is going to be plus x velocity with our x value, or x position rather. Basal x position. bad Austin Powers reference for anyone familiar with the genre of spoof spy movies. Let's run that and see what happens. If everything has worked, we should be able to move backwards and forwards. Awesome, backwards, forwards, backwards, or forwards, backwards, depending on your perspective, I suppose. Let's do it now so that we don't forget. Movement acceleration. So movement acceleration. So what I'm going for, I was doing some research into how good platformers or how classic platformers do movement, and one complaint a lot of people have is when the player kind of skids and the movement isn't very tight. But it is also nice to have a small amount of acceleration, so you can move a tiny bit by tapping keys rather than instantly moving at your maximum speed. So we're going to try and we're going to play with some numbers and try and get something that looks or feels nice. Max movement speed. Let's have a max movement speed of 2 for now, and let's change this to 0.66. So let's do it for one direction now and see if this makes sense. Similarly, we are going to want this is where we're going to want a clamp function or something like it. Let's just go back to a state where stuff works. There we go. Clamp is going to take 3 values. It's going to take n, min n, and max n. And what it will do is, if n is between these values, then it will return n. Otherwise, if n is lower than min n, it will return min n. If n is greater than max n, it will return max n. Probably easy just to start with a condition again. So if n is less than minimum n, we are going to return min n. Oops. If n is greater than max n, we are going to return max n. Else we're going to return n, and this will let us easily update our x velocity so it's in between 0 and our maximum movement speed. So we are going to clamp x velocity plus, clamp x velocity plus, what did we call it? Something like movement acceleration. Get rid of wrapping because we hate wrapping. X velocity plus movement acceleration, and then the minimum is going to be 0, maximum for this is going to be max movement speed. Let's see if that works. I'm not as confident this is going to work, but we'll see. Okay, cool. Now let's do the same thing for the other direction. Code is starting to look pretty ugly here, but we'll neaten it up in a moment, because we're basically doing the same thing to all of these values. We're applying an update to a value if a certain condition is true, otherwise we're leaving it alone. So yep, movement acceleration. So this is, we're moving to the right here, so this is negative values. That means our lower value is going to be negative max movement speed, and our maximum value is going to be 0. Okay, there we go. So we've got some basic movement functions, and the important thing is that they depend mostly on these values, or hopefully entirely on these values, unless I've hard-coded any numbers, which is a bad idea because you come back to them later and you're like, what does this number mean? Why is it here? So later on, when we want to tweak how our controls feel, we can come back, we can edit these numbers, we can make the player move faster, accelerate more or less fast when they're falling, running left to right. Basic platformer stuff. The next thing, well, two things I want to look at. One is jumping, and one is actually landing on stuff. So landing on stuff requires some basic collision detection. Let's do that. And we should be able to do that in a pretty simple way, because PlayCLJ gives us a whole bunch of functions for working out if rectangles overlap with each other, and that's basically it's where we're going to start our collision detection. Eventually we might want to make it a bit more advanced, but to start with, we're just, everything is behind the scenes, everything is a rectangle. If the rectangles overlap, then a collision has happened. Let's make a platform. This is going to look a lot like our player function to start with. Like I said, to start with, everything is just going to be a shape. Eventually, we'll have arts and all of the other nice things that you know, you'd see in your AAA+ title. But until then, rectangles. Rectangles are awesome. Cool. We could pull out a function here for making shapes. We do, you know, making shapes, dancing on the dance floor, making shapes, but we only do it twice, and we're not going to do it forever. So at the moment, we're not going to. X is X, Y is Y. There's not going to be any velocity at the moment. We'll worry about moving platforms later because it requires a lot more maths. What we do want to do though is we're going to introduce this is idea, and this is the hero. This is a platform. And the reason we're doing this is because down here where we update our logic, where do we update it? Down here where we update our logic, we need a way of working out whether the thing that we're updating is a platform or whether the thing that we're updating is a player. In fact, if I run it now, if I add the platform and then run it, it will blow up because platforms don't have velocities. So let's just prove that that's the case, and I'm not talking lies. MK platform. X, that's 10, 10, 400, 50. What color did I make? I just want to check that I made a different color. Yes, I did. And this should blow up if we are correct. Awesome, stack trace. One of the downsides of a Clojure is it has terrible stack traces and error messages. But if we dive in here somewhere, yeah, in update, it's complaining about update velocity because platforms don't have velocity. Or to start with, we only had one thing. We only had the hero to worry about. But now we have many things to worry about. That's going to require us to make some changes down here. Right, to start with, we want to actually because it looks nicer. Let's create an is function, and this will take an entity and and a name for the entity, and it will return whether the is key on the entity is equal to to its name, or to the name we're checking against. So we're introducing a concept. I guess if you were coding in Java or a language with interfaces, this is where we would enforce an interface on everything. But we're not going to do that. We're just going to trust that we remember, at least at the moment, that we remember to give everything an is key. So here we can say if is entity hero. I think we called it a hero. Let's just check. Hero. Cool. So we are saying that let's just fix the indentation. If the entity we're mapping over is a hero, then we want to run update velocity and apply velocity. However, if it is not, we're just going to return it. And what this means is that the platform will pass through this function and nothing will happen to it. The same platform will come out the other end. But if it's a hero, then we're going to update all of the hero's values. And let's just run this and check to see that it works. Cool, there's our platform, there's our player, and we're going to fall straight through it at the moment because we don't have any collision detection, but it works, which is the important thing. Sweet. So now we're actually going to extend what these methods look like, or change these signatures of these methods. So they're going to take a single entity, and they're also going to take a list of all of the entities. And it's important that these guys have the same method signature, or at least that they all start. All of their methods start by taking in an entity, because down here we're using this threading macro, which I should have explained when I first used it, but I didn't. What this does is it takes the the first argument, and it makes it the first argument of all of these functions and passes the results of the functions into each other. It's a way of making code look nice. We can kind of explain it over here if we go to the REPL. What we could do is we could start with an empty map and set x to 10. Sweet. Then if we wanted to update that map again, we could take that entire map and set y to 5, x10, y5, and if we wanted to update it again, we'd have to take all of that, do that, set z to, I don't know, 15. That gets really messy. That's really hard to read. So what you can do instead is you can use one of these guys, start with the empty map, then this version of the arrow uses the first argument of your functions. It basically fills in the first argument for you. So the first argument to a sock is normally a map, but we don't have to provide it because we've pulled it out. So empty map. Then we're going to say sock x10, sock y5, sock z15. Same result, but it is nicer to read. Hey, MXCK, mzk, however that is pronounced, gave the pop filter a workout there. Cool, where were we? Right. So these guys, they have the same signature, but we need to actually provide the entities. I'm not sure update velocity needed the entities, but we'll, if we don't touch them, we don't touch them. Yeah, that's fine. So in apply velocity, where we now have all of these entities, we are going to, so we know we only ever call this on the hero, so let's change entity to be hero. We're just doing this now because it'll make it easier to read when we come back to it, and it will stop my brain melting quite as much as it is. Hero, hero, hero. I could have been smart and used a find and replace there, but then it would have changed it in entities as well, and it just would have been horrible. So cool. Hello, SpongeBob Boy 11. Hello to you as well. Your name is a particular shade of green, which is really hard to read on my monitor. Congratulations. What are we doing? Applying velocity. Yes. So we only want to apply a velocity if, basically, if the player isn't going to overlap with a platform. So let's start with the y value like we did before, and we'll come back and do x afterwards. So our new y velocity is going to be that. So rather than doing it automatically, we want some kind of check. Right, this is where we need to get let's just call this collisions. Pull out a function, and this will take yeah, it's going to take our hero, and it's also going to take the entities again, and it's going to basically give back true or false. It will give back true if we are hitting a platform, false if we're not hitting a platform. And one thing we want to do is build a bounding box or a collision box for the player and the platforms. Actually, we want everything should have a collision box. Because the platforms aren't going to move, we're going to build the collision boxes for them when we make them, but for the player we're going to build the collision box as it happens.